Welcome everybody, my name is Rodrigo Virumbrales from University of Southampton, and today I'm going to be talking about performance estimations of flapping foils under unsteady upstream conditions. So this topic, something that you can really see in nature, which is that animals do collaborate in order to obtain benefits in their traveling performance. This is something that you can really see in fish schooling, in free flight formation. It's everywhere in nature. So we have this engineering equivalent that we call flapping foils, as you can see here, that basically tries to mimic the motion of a fish in order to achieve the same efficiency and propulsion. This is something that nowadays is being applied in a lot of scenarios. It's gaining a lot of relevance, for example, in micro air vehicles like the one you have here, which is a robotic dragonfly. The motivations behind this talk is that although there is a lot of literature about flapping foils, this literature is very limited to a tight range of conditions, such as low turbulence, low amplitudes and frequencies of motion, and mainly sinusoidal kinematics. So we think that we have to develop new, fast and efficient methods that can achieve a reliable real-time estimation of the flapping foil performance. If we want to apply these models into the real world, we have to be able to apply those in real time with real-time estimation. So this is what this presentation is about. So starting by the performance estimation of flapping foils, we can go to the very basics of the literature regarding this topic, which is the Theodorsen paper back in 1930s. I'll give you the references later if you want to check them. So what we have here, we have a solo flapping foil that is following a pitching and heaving motion, which we usually call couple motion. And as you can see here, this equation from Theodorsen paper is describing the instantaneous lift of the flapping foil. This has two main components. One is going to be the added mass component, and the other one is going to be the circulatory component. We can rearrange this equation. We are also going to introduce our parameters, the Theodorsen constant, the pivoting point, and we are going to put this value in the dimensionless coefficient, and we can reach the second equation, which is going to be the lift coefficient of this flapping foil. But what we can do here, we know that there is going to be a very important parameter in flapping foils, which is the effective angle of attack, which is basically a combination between the incoming flow, the pitching angle, and the heaving velocity. So we know that this angle is going to look something like this, and by applying the small angle approximations, we can introduce this angle into the previous equation to have something like this, which is going to allow us now to have the Theodorsen equation in terms of the effective angle of attack and not on the kinematics of the foil. And what we want to do, or we can do, in order to also calculate the thrust performance, we can go to Garrick's paper. Again, wait for the end for the references, which is basically a projection of Theodorsen's lift with the addition of a term in relation to leading edge suction. And then we can have our lift coefficient and our thrust coefficient both in dimensionless form and with effective angle of attack included. But this is only for a solo flapping foil. So what can we do in order to also be able of using this equation for a flapping scenario? Now we are going to have this case and we are going to focus on the heme foil. Now the sketch is going to change because now our foil is facing not a uniform free stream flow, but also the wake of the leader. So we have to sort of include the effects of the wake into the sketch that we have before. And we are going to do that with two main components, which are the vertical and horizontal velocities imposed by the vortex that we have called V gamma and U gamma. The good point now is that we can include those components into the effective angle of attack definition. There is going to look something like this, and then we just have to include the new angle of attack definition into the previous equation that we had. So now we have an equation that works for both solo and tandem flapping foils. It has to be mentioned that the original Theodorsen equation was developed for very low frequencies, low amplitudes of motion, and this is not really going to be our case, but it's still worth the try to see how this equation can adapt with the new incorporations in the angle of attack to other scenarios. We are going to compare this equation with another model, which is a simple quasi-steady approach that just considers the classical 2-pi alpha lift evolution. We are going to call our new model potential flow model in the following plots and results. All the results coming from this model are going to be referred as potential flow model. Just to conclude this method definition, you can find more information about the quasi-steady approach in this reference and of Theodorsen and Garrix in those other ones. So as a kind of validation, we are going to first look at all our results for a solo foil, and we are going to compare our estimations with both the quasi-steady approach and the potential flow model against an in-house CFD code called Lotus that has been validated in similar studies with similar approaches. So we are going to compare our estimations to the CFD results. On the plots, you can see on the top row the vertical force coefficient, on the bottom row the horizontal force coefficient, on the left column and a Struhal value of 0.3, on the right column and a Struhal value of 0.4. And all these simulations have been done with coupled motion, so pitch and heave, with the amplitude equals to the chord and with a Reynolds number of 7,000. And the first thing that you can see here is that the potential flow model is clearly improving the performance of the quasi-steady approach and is matching much better the results obtained by Lotus, which makes sense considering there is a quite more complex approach that takes into account things that the quasi-steady do not even consider. But the other thing that we can see is that as you increase the Struhal, the accuracy of the model decreases, which again makes sense considering that higher Struhal means higher frequency, which means that we are farther away from the original scope of the equation that is the basics of our model, which is Theodorsen equation. So once we see that we can get sort of accurate results for a solo foil, let's go about how are we going to implement this model for a tandem approach. So we have called that virtual hint model. Why did we do that? So first of all, in the classical tandem simulation, what you are going to do, you are going to model both the fore and the hint foil. So you are just going to have two foils and you are going to calculate the forces in both. But what we can do, we can place a probe, it's just a numerical probe, that is going to be in the leading edge of the hint foil. And what we can do, we are going to run simulations that are going to consist in a fore foil and the virtual hint probe. So we call that virtual method because now instead of just modeling both foils, we are going to model one foil and we are going to place a numerical probe in the flow that is going to mimic the hint foil. So it's going to look something like this. Obviously the circle is just for you to see where the probe is going to be, but we are not really placing anything inside the flow. The good point is that at this probe, we can calculate the velocities imposed by the wake, that if you remember from the previous slide, is going to be enough to calculate the new effective angle of attack. There is going to be enough to obtain the new forces performance of the tandem foil. And not only that, but also the fact that this probe is numerical, is not interacting, is not affecting the flow, allows us to place not one, but multiple probes in the flow. So with just one simulation, we can place multiple probes that are going to mimic multiple hint foils, and with just one simulation, we can have n tandem results. So we are going to have, each of the probes is going to have a spacing or a phasing with respect to the fore, and hence we are going to have, with just one simulations, n different tandem results, which is going to decrease greatly the computational effort. So now let's take a look to our results. About the performance estimation of the tandem, I'm going to present the results in terms of the phasing and spacings between the fore and the hint foil, the longitudinal spacing and the interfacing between the motion of both foils. And the first parameter that I'm going to show is the average cycle thrust parameter. I have called it CX star, which just represents the average thrust developed by the hint against the average thrust developed by the fore. Both foils are forward same kinematics, so if this value is greater than 1, that means that our hint foil is having a benefit from the tandem operation. Obviously the opposite if the value is lower than 1. So let's take a look. We have on the left our estimation with the potential flow model. On the right, we have the Lotus result. Top row is Struhal 0.3, bottom row is Struhal 0.4. The first thing that we can see is that the estimation is accurately capturing the areas where the hint foil is having a benefit or a penalty. The benefit are the red areas, the penalty are the blue areas that follow this very characteristic valleys shape. And also we can see how, as you increase the Struhal, this value is being underestimated. Again, just in relation to the solo foil, the model is performing worse as you increase the Struhal. Anyway, this potential flow estimation is by itself a great, is performing with a great increment in terms of accuracy than if you compare with the results obtained by a quasi-steady approach. You have more information on this reference, that is all at the end. But the thing about those results is we have the feeling that we have to be careful. Why? Because if our model is obtaining a similar cycle average value, that doesn't mean that the model is going to be accurate in the real-time estimation. And in order to illustrate that, we are going to take a look to two cases. The first one is going to be a high performance case, so the one in the red area, and the second one is going to be what we call low performance case, the one at the blue area. So taking a look at the time signals of some parameters in these two cases, high performance in black, low performance in red, we can see the very first thing that we can see is that the high performance is much more stable than the low performance. The readings on the left, we have the vertical velocity imposed by the wake. On the right, we have the horizontal velocity imposed by the wake as well. So this is the first thing that we can see. And this has a very simple explanation. If we take a look at the tandem simulations, here, of course, we have two foils in order for you to see better what I am talking here about. So we see that in the high performance case, we have the hint foil waving among the vortices of the leader. So the hint foil is only touching vorticity structures twice per circle. So the two times that the hint foil crosses the shear layers. And this is giving us these two changes in the black lines that you can see here. But on the other hand, the low performance is constantly hitting vorticity structures during the wake, which is causing the signal to have these huge increases and decreases that are causing the instabilities in the signal. And how is that going to affect to our force performance estimation? Let's take a look. On the left, we have the high performance. On the right, the low performance. On red, we have the Lotus result. On black, we have our potential flow model or adaptive Garrick results. And you can see that the high performance is performing much better in terms of estimations than the low performance. And this is basically because our model still have some quasi-steady component in the circulatory lift component that obviously cannot deal with the huge instabilities that we are having in the low performance signal. But if this signal is more stable, as it is on the high performance, you can see that the accuracy of the model is much better. But still, this is not enough. If we want to apply this model to a real case scenario, we have to be able to be accurate for any case. So what we are going to do next, we are going to apply some machine learning techniques in order to increase the accuracy of the model. So as a conclusion, we have developed a new propulsive method that is based on the classical Theodorsen equation that has proved to be accurate for a solo flapping foil and for some cases of the tandem flapping foil case. So after that, what we are going to do, we are going to apply new approaches, mainly based on machine learning, that are going to hopefully increase the accuracy and are going to allow us to apply this method in a real case scenario. So lastly, here are the references if you have any doubt and you want to consult them. And apart from that, thank you very much for listening. I am open to your questions. Thank you very much.